Welcome students, we're going to be covering exponential and logarithmic models today, and the key idea behind this is that we're just applying some of the principles that we've learned. So primarily this is going to be the ideas of graphing. We're actually only going to cover a few of the examples in class, and only a few of those will show up on the test. The other part of class will be spent discussing what will show up on the test and how to properly study. Now note, there will be homework today, so you can always prepare for that. With that said, what I would like you to know is that there's biblical integration this week, and that is what concepts from this section, from this chapter, play into biblical integration. And what I would like to say, this is the connection, that as humanity we like to predict things. We like to make predictive models. And this is even seen throughout human history. They used to use divination, now we use scientific models, but nevertheless we are predicting things. And what we've learned, clearly, through human history, is that our predictions don't tend to work out. When you've predicted when the bell goes off and you get it wrong, you keep trying again. But there's this instance in the Bible with predictions, or rather with how the future goes. God has it established. It's not a question of if, but when. So with God, the certainty is there. Now this means that his models, his predictions, are also, in a sense, not time dependent. He doesn't sit there and say, well, this day, this year, this will happen. He tells people that these invaders will come and take all your people. And so surely it does happen, but it is almost the sense of there's an anticipation for what will happen. So anyway, what I would like to say is the biblical integration is this concept. This is certainty, just as we can model the future in hopes to prepare for it. So we can model it. We look at God's model / his plan as a certainty. His promises. So this is the idea, because in exponential growth, the idea is that we model what will take place. So if we model what will take place with exponential growth and other things like this, we should also take into note that we can prepare for it. We can model the future in hopes to prepare for it, but we can look at God's as a certainty. Okay, so let's type in some of these. So exponential growth model is y equals ae to the bx, where b is greater than 0. We're just going to turn everything into a equals a e to the negative bx. So this is going to be same thing where b is greater than 0. And this is going to be the negative, so it's going down. Growth goes up. Gaussian, you do not need to know. I'll type it in. This is for statistics. You don't even need to know this for statistics. This is just the model. Okay, that's the Gaussian model. Don't worry about it. You don't need to know it. Logistic model. Okay, that's logistic growth, and logarithmic is y equals a plus b ln, b ln of x, or y equals a plus b log of x. Okay, these are our different models. You should know the graphs of them and kind of how they relate to specific types of problems, okay? So you can pause the video. Again, this biblical integration will be a question. What I would say is in class we'll talk about verses that we can, so no, I would say hint, no verses that point us to this, okay? Okay, we're going to talk about growth. So, example 1 and 2. Example 1. So notice that this is growth. This is going up. So this is a growth model, and this is the years. So this is linear. This is not going to be linear, and they give us the number. If you can't read it, it's here. So S equals 10.33 e to the 0.1022t, and this is for 7. 7 is less than or equal to, t is less than or equal to 11. Okay, so that's right there. Estimated billions, t is 7, represent 2007. So you try to figure out when you'll reach $40 billion. So if we're doing that, we put 40, I believe actually this, maybe I'll just put it on the paper, it'll be easier. My apologies. Okay, so what we're going to do is we're going to set it up 40 equals 10.33 e to the 0.1022t, and we're going to solve for t. So this would involve the step, you're going to take natural log, so it would be natural log of 40 divided by 10.33 equals to 0.1022. And then solve it out, okay? Okay. So that's gonna be the plan right there. And we'll solve it for t. Now this one, in a research experiment, a population profile is increasing according to exponential growth. After 2 days they're 105, after 4 days they're 300. So we get two different points. We get 2, 100 and 4, 300. Okay, so we're trying to find out 5 days. So this gives us the equation. 100 equals a e to the 2b, because time times b, and 300 equals a e to the 4b. So what do we do to solve this? Well, we actually can set this up as to solve for a here. So if we do that, we get a equals equals 100 divided by e to the 2b. Okay, so then we plug that in here, so we get 300 equals 100 divided by e to the 2b, because I substituted, times e to the 4b. So what cancels out here is the e's, e to the 2b and e to the 4b. So then we get 300 equals 100 times e to the 2b, solving it so that it's, we get 300 divided by 100, which is equal to 3, equals e to the 2b. How do we solve this? We take natural log of both sides, so natural log 3 equals natural log of e to the 2b. Solving this out, we get natural log of 3 equals 2b. So then b equals natural log of 3 divided by 2. Okay? And then you can plug this in to this to solve for a. Okay? Where it would be a equals 100 divided by e 2 times ln of 3 divided by 2. Okay, you can definitely solve this right here. Okay, this 2 and the 2 is going to cancel. It's e to the natural log of 3. So then a is going to equal 100 divided by 3. Oh, wait, hold on. 100 divided by 3. There we go. Okay. And so then what is our question? How many flies will there be in 5 days? So we'd have 100, y equals 100 by 3 times e to the 5 times, times ln 3 divided by 2. And you can solve that. Okay? That would be our answer. So that would be how we solve this. Okay? Okay, I'll come back for the rest of this. We'll only do example 6 for now. Okay?